5. So chapter 2, limits. What you're doing in the lab is actually just getting an idea of what this definition I'm going to give you says here. It says, oh, here we go. These are my old notes. Switch back to my other one. That's too bad. Okay, there it is. So this should be the first one on yours. It's right under the limits. This is the definition of a limit. It says, let C and L be real numbers. The function f has limit L as x approaches C if given any positive integer epsilon. That was the green band. So you hand me any interval, or any interval, basically. Epsilon is a number. And so you take that epsilon, it can be as small as you want, you add it to the limit L, you subtract it from the limit L, and you create an interval. Okay? That was that green band in the computer lab. So you hand me any one, as small as you want. You can get crazy. As long as I can find a delta, a number delta, such that I add it and subtract it from the C value that goes with the limit that we're testing, I create another interval. If every number in that interval, when I plug it into the function, stays within the green interval, then we successfully have a limit. And limit is L. Okay. So that's the idea behind this. Hopefully you kind of have a visual of it. I tried to draw it here last year and try to explain it, and you looked at me like I was crazy. So I found this Geometry Sketchpad thing that I thought actually demos it better than anything I've seen so far. So this is something that I think I went through many semesters of calculus before I ever got it. I don't think it was until my analysis course that I really understood this definition. That was after taking 3 semesters of calculus. Yeah. So it's all these, I learned all these skills. I even found epsilons and deltas, and really I don't think I understood what it meant. But anyways. So don't panic if you're having trouble wrapping your mind around it. But that's the idea behind the limit. And so that's what allows us to have a limit to that function with just a hole in it. I can get as close to that hole as I want. I can always find a delta neighborhood about C that's going to completely map into that, we called it a neighborhood, epsilon neighborhood about L. But with the jump, I cannot. So if you go back over here, where my jump is, anyways, we'll find the jump. I got an example of the jump here. But so if you think of the second sheet that you looked at with that jump, the limit did not exist. Now we are going to talk about one-sided limits. Did you talk about those at all last year? One-sided limits.
Yep.
So one-sided limits, we can look at those if the one-sided limits don't match, then the limit of the function doesn't exist. We talked about that. That's kind of like the working man's way of checking if the limit exists. So a limit is simply the expected y value of function reaches. Probably Mr. Gluck told you that last year, but it's the expected value. So how can a function with a hole in it still have a limit? Well, that hole is the expected y value. I can get as close as I want to that. I expect it to go to that spot. And so you can your limit is just a number. It's a real number. It's the y value. So what is a limit? A limit is the expected y value a function reaches. A limit only exists when both the limit from the left and the limit from the right are equal. Like in this example, you have a picture of this one. It's the second one on there. This is a nice continuous function. This could be an example of a function that does not have a derivative at x equals 0, but it does have a limit. If you notice here, the limit as x approaches 0 from the left, this is the way we write it. You've seen this notation before. The limit, and then underneath the limit we have is x approaches 0. There's a little minus sign on there. That means as x approaches 0 from the left of f of x, whatever the function is, equals 1. That's the y coordinate that corresponds to an x coordinate of 0. That's our notation for limit from the left. And then the limit from the right, the notation looks like this. Limit as x approaches 0 from the right of f of x also equals 1. So therefore, the limit exists, and the limit is 1. So very subtle differences here. This is limit as x approaches 0 from the left, from the right. And this is the limit at 0. So it's kind of, yeah, this is what we mean by approaching from the left. And really I could have an arrow approaching from the right. Do you have any questions on that? All right. The next example I want to do is this one. Do you have this one next? Yeah, I reordered it and it reverted back to my old version here. What we have here is kind of like the example you saw in Geometry Sketchpad. We just have a hole. That's it. The limit as x approaches 1 from the left of f of x would be what in this one? -2. And the limit from the right, also -2. Therefore, the limit of the function is -2. So our first function we saw was a nice continuous function, no holes in it, no jumps. This one has a little bit of a hitch in it. It's got a hole, but it still has a limit just like the one before it did. Then the third example I wanted to look at was the one with the, if you flip it over to the next page, the jump in it, which was this one. Now this one, as you saw in the Geometry Sketchpad one, is not going to have a limit, but it does have one-sided limits. If I just look at this limit as x approaches 3 from the left, we see that the limit is 3. And the limit as x approaches 3 from the right is 6. Therefore, the limit as x approaches 3 of f of x, we use d and e. Did you use that last year? Does not exist. And if you were asked to verify that, you could simply say it's because the limit as x approaches 3 from the left of f of x does not equal the limit as x approaches 3 from the right of f of x. That's it. Quick way with mathematical terms of saying, or you could say it in words. That would be okay. In words, that's allowable. So those are really the three primary cases there. We had a nice continuous function, we had a hole, and then we had the jump. I kind of see the one with asymptotes in it, kind of like a jump there, at least at that point where the asymptote is. When we talk about the one-sided limits, that one differs from this one because you're going to be going either negative infinity or positive infinity. We'll talk about that when we get to limits at infinity. Maybe next week. All right, any questions on those three examples? So we can calculate a one-sided limit. We can decide if a limit exists, at least visually. We have some properties of limits here. Right here, and that should be on the next slide on there. Properties of limits. If L, M, C, and K are all real numbers. So L is a real number. It's actually the y value of the limit of one function. M is the y value of the limit of the other function. C and K are different. Well, either different specific numbers. K is actually a scalar. But the properties of limits. Here's what it says. If you want to go ahead and find, say you have a function like x cubed plus 3x, you could find the limit of x cubed plus 3x by substituting in the number in question. That one's not going to have any problems. It's a nice continuous function with no holes, jumps, or asymptotes. But if you were to find the limit of that function, you could plug into the original function, or you could find the limit of the x cubed part, and then find the limit of the 3x part, and then add them together. That's what this is saying. So the limit of the sum of two functions, if you could break it up into a sum, is the same as finding each individual limit and adding them up. The limit of a difference of two functions would be the same as finding the individual limits and subtracting them. The limit of the product is the same as finding the individual limits and then multiplying them. The limit of a scalar multiple times that function would be the same as finding the limit of that function and multiplying it by the scalar multiple. And then finally, as long as the one on the bottom does not have a limit of 0, which it could. 0 is a valid limit. Then you could find the limit of, look at a rational function as the limit of 2 separate functions and then divide. And probably when you evaluated these by substitution, you didn't even consider the properties. Have you seen the properties before? Or maybe you've seen them. Okay. Basically, this is saying all 4 operations plus scalar multiplication works with limits. That is not necessarily true with other operations that we're going to be looking at, like differentiation and integration, as well as many other operations in mathematics. So the question is, in math, a big question in mathematics is, you know, with this property, with this idea of limits or differentiation or integration, or like with matrices, did you study matrices? Okay. Well, matrices are not commutative. Right? Matrices are not commutative over multiplication. You know, the order matters. So the big question here is, you know, can I do the 4 operations with limits? And the answer is yes. Yes, you can. So you can almost skip. You could pretty much just do whatever you want to do with them and separate them out in whatever way you want. So if you look at the last slide on there, you got a bunch of examples really small on there. These you might want to do on a separate sheet of paper. I don't know how you want to go about that, but I'm just trying to get it on the back to back. So maybe, or on the lines in there, you might want to do these examples. But I have 5 examples to do that are going to show 4 different techniques for evaluating the limit. And I know you've seen probably 3 of them, probably 4 already. So the first one is direct substitution. Everybody likes this one. You have like 1 problem in your homework on this, maybe 2. But hey, you can substitute in, right? And if I substitute 2 in here, I get 21. So that's the first thing to try. Just try direct substitution. If it's a nice continuous function, or if I'm asking for the limit at on a an interval where it's continuous, then it's going to give you the limit directly. Just plug it in. So you probably did some of these out. But that's not always the case. Look at example 2. What happens if I plug 2 into example 2? Yeah. The limit is always the y value that you would get if you plug the x value right here into the function. Yeah. So the limit is always asking for the y value, not the x value, but the y value. This one is it's not really even. It actually 2, 21 is a coordinate on the graph of it because there's not a hole or anything. It's not like you're just approaching it. You actually get there. Now here, what happens if I plug in 2? Yeah, divide by 0, and that's not bad enough. Yeah, I got 0 on the top too. That's an indeterminate form. So if I plug in 2 here, by substitution, I get 0 over 0, and we call that an indeterminate form. There are many other indeterminate forms. I think you'll recognize them when you see them. But they can all be kind of broken down into, algebraically, you can rewrite them, I don't know, you can rewrite them as typically 0 over 0, something like that, or infinity. But there are lots of indeterminate forms. In your book, they might list some others. But if you get 0 over 0, what you have to do is go back to the drawing board. You have to do some kind of algebraic simplification. I think you probably did this last year. So I have limit as x approaches 2 of, can we factor this thing? 2x minus 1 and x minus 2, okay, over 3 x minus 2. So we factor those things, and we factor them expecting maybe to cancel something out, otherwise there's a problem here. So cancel those out. That's called a removable discontinuity. This would represent a place where the graph has a hole. This graph also has a vertical asymptote. Where's the vertical asymptote in this graph? Can you tell me by looking at it? Yes, it would be what would make the bottom 0. That can't be removed. Why is this not a vertical asymptote at x equals 2? Yeah, we can remove it. It's called a removal. So when you can if you can factor and cancel out something from the bottom, that's just a hole. If you can't cancel it out, you've got a vertical asymptote. So what happens when I cancel that out is I have limit as x approaches 2 of 2x minus 1 over 5x plus 3. And if I plug 2 into that one, I do get a limit 3 over 13. So can you tell me where on this function I have a hole? What's the coordinate of the hole? No, not negative 3/5. X equals negative 3/5 is a vertical asymptote, so there'll be no y value to go with that. No, it's going to be at 2, comma 3/13, right? That's where the hole is. That's you need to know that later. We're going to be doing what are called extended functions, where you got to fill in the hole. So you'll have to label the hole. You know, you'll just say at x equals 2, this function equals 3/13. That fills in the hole. How did you find the hole? How did I find the hole? The hole had to be whatever corresponded to, whatever y value corresponded to the x value that got canceled out. So since the 2 is the value that got canceled out, that's where the hole is. So I was actually asking for the limit at the place where the hole is, kind of like we were doing in your geometry sketch that thing. And that value, that y value is 3/13. All right. So we have substitution work sometimes, and then you're going to have a whole set of problems. There are actually several where you got to do some algebraic tricks. You may have some questions. Do their best. I don't know in terms of what you remember from algebra, but you're going to be doing some factoring and canceling. If you see a complex fraction, find a common denominator, flip, and cancel. If you see problems with trig in it, you might be replacing the trig step with other trig identities and then canceling and then replugging it in. You may have some questions on it. Do your best on those. But I don't know. I'd have to do a gazillion different examples to cover every possible algebraic simplification. The one you've probably seen before, and you'll see the most of it is probably this factoring. So we'll see how you're factoring and remembering stuff. I think there's even one in here where there's a cubic. You know, factor like x cubed minus 1. Take the cube root of each of those, and you match the sign. So it'll be x minus 1, and then in parentheses you'll have a trinomial. X squared. Yes. Well, it's square the first, x squared, and then opposite sign, and multiply the two things in parentheses. So plus 1x, and then plus 1. So just do factoring cubic. But there'll be a cubic in factor. I think it's in this assignment. So anyways, see, that goes in. There's GCF factoring and that kind of stuff. So have fun with your factoring. But expect to cancel. That helps with your factoring. All right, the third method here, which I think you probably did last year, this is probably where you stopped, is what if I can't simplify it algebraically and cancel it? Could it still have a limit? Yes, it could. How do I find that limit? Graph it. Here's another method. Graphing is a viable method for finding the limit. Graphing, and we might have to look at the table. So here's a function. Limit as x approaches 0, tangent x over x. If I plug in 0, I get an indeterminate form. Just verify that. 0 over 0. So actually it's, let's see, yeah, 0 over 0. So right here, I could change it out and change sine to sine x over cosine x. That's not really going to help. Right. So my only other choice at this point is to go ahead and graph it. So let's go ahead and graph this on our graphing calculator. Change x over x. Make sure you're in radian mode. And then also, if you want to graph a trig function, you should do it in the Z-trig graphing window. If you go to Zoom and it's number 7, I think that might be helpful. But make sure, go to mode and make sure you're in radian mode first, and then type in tangent x over x into for your y1. So we have, make sure I'm in the right mode here. That's good. So tangent of x divided by x, and then hit zoom. And I like to use z-trig if I have trig functions involved, use z-trig. And what z-trig does here, try that again. Tangent of x divided by x. You can go to zoom, number 7. So, no, please. So, right here, what does it look like visually? The limit is at x equals 0. Looks like it's 1, right? Now, sometimes the graphing calculator lies, but we don't see the whole story. Things could be happening there about 0 that you just don't even see. But the other option you have here is to go to second, and then go to table, and actually go to second table set. You might want to do this. So go to second table set, and table start, we're going to put it at 0. So go to second table set, put table start at 0. What that does is starts your table right where I want to evaluate the limit at 0. If, say, the limit we were evaluating at 2, you might want to start your table at 2. Here's why. When we use the table and limits, we want to make a very small increment here, delta table, because if I'm going to use the table to evaluate the limit, I need it to stay real close to that value. So I'm going to start with 0.1 and see if that's appropriate. So maybe put 0.1 in for the delta table. Go to second table. At 0, I have an error. To the right of 0, I have a value of 1.033. Let's see how close we are on the other side of that. So if I arrow up, look at that. So I don't need to make the delta table any smaller. You can see right here, on each side of the 0 with an increment of 0.1, they already match. So what does that mean is happening? It's converging. Yeah, it's coming in on 1. Yeah. Now, if these numbers maybe were different, you might want to make your delta table 0.01 and see again. And then you can keep making it smaller and smaller. Yeah.
Maybe the table type or worse type.
Go to second and then window. So that's the third method for finding a limit. Now, let me show you one other thing here. Believe it or not, okay, so we said the limit was 1 here. That's just by using the graph. Okay, so we okay with that? Using the graph or using the table. You might have to use the table sometimes. You can't always tell from the graph. There's actually a way to do this algebraically. Let me show you that. Limit as x approaches 0. Would you agree that tangent can be rewritten as sine x over cosine x, right? And then I have on the bottom of this x. Now, if I rewrite this again, I'm going to rewrite this as sine x over x, and then I'm going to take this cosine of x and just leave it on the bottom here. These two are in fact equivalent. Here, maybe think of it as x over 1. Flip and multiply, you see it now. So the x lands on the bottom with cosine, sine stays on the top. Now, using the properties of limits, I can go ahead and break this up into 2 limits, which we will both know. The first one is limit as x approaches 0 of sine x over x times limit as x approaches 0 of 1 over cosine of x. What I'm doing is breaking this up into sine x over x and 1 over cosine of x, and there's a reason for that in a minute. You're going to have to memorize a fact. Limit as x approaches 0 of the function sine x over x shows up quite a bit in calculus, and that limit is always equal to 1. I'm going to show you how I know that right now. If you graph, go to y equals, I'm going to go ahead and graph sine x over x. There it is. It kind of, see how that's 1? So the limit as x approaches 0 of sine x over x is always 1. You might want to star this. You're going to have to memorize it. In your homework, I believe there's one that can be done algebraically like this. 1 or 2 of them. So this is always 1. So what my properties of limit say is that if the limit exists for each of these two, if they're each real number limits, I can find the limits separately and then multiply them. So if this one I know is 1, and this one if I plug in 0, cosine of 0 is 1. 1 over 1 is still 1. And so my limit ends up being 1. So this would be the algebraic way of doing that one, which you would only be able to do if you know this fact. Limit as x approaches 0. Sine x over x is always 1. Go ahead and box that or start. You need to know that. You're going to have to memorize it. It's actually something you're supposed to know for the AP exam too. That could be a rewrite. What's that? The one right here?
Yeah.
Or this one?
Yeah.
Oh, this one here?
Yeah.
Okay, cosine of 0 is 1. And 1 over 1 is 1. Yeah. We graphed this, and it had, I know this is confusing, because we graphed this one, and it had a limit of 1. But then the overall limit of the tangent x over x, when we graphed that, it was also 1. That's not always. But sine x over x, the limit as x approaches 0, that is 1. Don't get that confused with the limit as x approaches infinity of this same function. What does it look like the limit is as it goes to infinity? It's like it's closing on 0, and you take that. All right, so those 3 methods, you have substitution, algebraic simplification, graphs and tables are legitimate ways of solving limit problems. And then there's one more that's new. It's called the sandwich theorem. This is another look at the graph. We could look at the graph of this real quickly. Let's do it. Do you have that one on there? It should be listed on there as you know before. So this one, if I go to absolute value of x over x, does anybody have a guess as to what that is without already graph it? So it's absolute value of x. Do you know what that function looks like? It's a salt and pepper one. It's either -1 or 1. Salt and pepper, -1 or 1. One or the other. Actually, salt and pepper I think bounces back and forth. So sorry, this is not salt and pepper. Salt and pepper actually bounces back and forth. Well, this one has no limit. You see why? It's not oscillating though. It's actually bouncing back and forth discrete. The calculator connects them, but they're actually discrete points in that function. So here we have it's either 1 or -1. There's no limit here at x equals 0. There's a limit everywhere else. But at x equals 0, there's no limit. So right here, there's a limit. It's -1. Here, there's a limit. It's -1. Over here, there's a limit. It's 1. But the limit as x approaches 0 does not exist. And you can see that pretty easily from the graph. So this one is a DNE by the graph. Now I can show you the sandwich theorem here. Here's how the sandwich theorem works. We can sandwich a function between 2 functions with known limits that are equal to each other. So if I can take this function x squared times cosine of 1 over x squared and sandwich that in between 2 functions with known limits, and those 2 limits are equal to each other, then that limit has to match it. So what we're going to do on this is start with the statement, and you're only going to apply this to functions with cosine or sine. That's the only applications of this we have in here. But for cosine and sine functions, they are what we call bounded. So whether it's sine or cosine, it doesn't matter. But would you agree that the cosine function is always going to stay on the unit circle between 1 and -1, right? Now, That in and of itself would not be enough to guarantee a limit, because if I were to evaluate the limit right here on the left-hand side, this limit of a constant function is going to be -1. If I were to evaluate what's the limit as x approaches 0 of -1, what's -1? What's the limit as x approaches 0 of 1? It's 1. So these are different limits, but I really want to know the limit of something x squared times cosine of 1 over x squared. So I start with this statement. Now doing a little bit of algebra, I can multiply through by x squared. So you start with a bounded function. You multiply through by x squared. So now what the sandwich theorem says is that if this function in the middle is always between these two, well, it's between these two at least close to x equals 0, and if I can find the limit of each of these, and they're the same thing, then the limit of this matches the limit of these. So you probably need to see a picture to see that this bounds this. That's what I had up here in the beginning. So let me, back to the graphing calculator. We're going to type in negative x squared. You can just watch this. And I'm going to type in positive x squared. And then I'm going to also type in x squared cosine of 1 divided by x to the squared, right? And I'm going to graph all three. It's showing up there. So there's one of them. That's negative x squared. There's positive x squared. There it goes. I don't know if you can completely tell, but this is sandwiched in between the blue and the red. Yeah. So would you agree that it is bounded between those two? So if I can find the limit of each of these, let's go ahead and run the limit. Limit as x approaches 0 of negative x squared, and then run the limit through each of these. Limit as x approaches 0 of x squared cosine 1 over x squared, and less than or equal to limit as x approaches 0 of x squared. What's the limit as x approaches 0 of each of the things on the ends? Just a little bit of algebra. All I'm doing is applying the limit to each of the three parts, right? Keeping it in balance. About the writing. So what's the limit as x approaches 0 of negative x squared? 0. And what's the limit as x approaches 0 of x squared? But that statement right there, what does that tell you? The limit as x approaches 0. 0. Yeah, that's what the sandwich theorem says. You know what these three dots mean? Therefore, that's a therefore. Only 0. So what we did is we started with the boundedness of this cosine of 1 over x squared. Now that in and of itself would not make me have a limit. I have to have a polynomial out in front of this function guy. It's going to have to be x or x squared or x cubed or something to have a limit. So right here is enough. I start with the fact that it's bounded. I multiply through by whatever's in front of the cosine or sine function. Then I apply the limit, and then I apply the actual sandwich theorem that says, hey, if it's between 0 and 0, it is, in fact, 0. Okay. So you're going to try, go ahead and turn the recording. I have you just try a few problems in class, and then you do have homework tonight.